Yes, so welcome, Marcin. Marcin is our second time presenter, and he will tell us about model serving with FastAPI and LitServe. So the floor is yours.
Thank you very much. Thank you for having me for the second time. Let me check whether it works. Okay, it works. So hello everyone, I'm Marcin Zabłocki. Right now I'm MLOps at Printify. I do machine learning for 5 or 6 years already. I've started being MLOps before there was even this thing called MLOps. I was ML engineer back then, apparently doing too much Terraform, so I became MLOps instead. And I also conduct YouTube channel with my colleague Wojtek, who is working in this very place, and we are actually recording one of the rooms across this room, basically. And what we'll be doing today? Today we are going. I've decided to take this opportunity that this presentation is in December, so it's a holiday season. So we'll be decorating a Christmas tree, and our Christmas tree is this FastAPI library. And our goal is to decorate this Christmas tree with our machine learning model. So we'll be basically putting this this star on top of our tree and I will show you how you can do machine learning model serving with FastAPI. So right now, raise your hand if you heard of FastAPI and if you used FastAPI before. Awesome. That means they did a great job. And usually when you ask over the internet in your favorite search why to use FastAPI, one of the first things that you see is this, because FastAPI is super performant. And when you compare it to Flask, indeed it is, because it's built on top of modern Python with async IO and so on. And that's the main branding for FastAPI, that it's super fast and efficient and performant. So the performance is basically that the performance that FastAPI has comes mostly from the fact that they use async IO, which is the modern way of doing input and output operations, which are super common in web servers, because you are constantly either reading something from network or writing something to network, or reading something from database or writing something to the database. So this is the most gains that you have from this async IO. It's super, super easy to use because you can start in like 16 lines of code that that you will see just on the next slide. And it's production ready because it's pretty mature, but I've deliberately put a star there because it's production ready for saving APIs. But for machine learning, it is and it isn't. And bear with me, I will show you what I mean. So let's see the minimal example of FastAPI server. So here on the slides, you can see like in 16 lines, you can already have a server. You just import a FastAPI library. You can let me use this one. You write your endpoints by using simple Python decorators. You specify what type of HTTP method you are using and the endpoint URL. And here you can see my super sophisticated offensive speech classifier that I've built. And basically, that's it from the FastAPI kind of a approach. It's super easy to start with, but as your project will be more and more complicated, as your models will grow in size, you will see some shortcomings. But before that, another thing that you have out of the box in FastAPI is validation, and nobody likes to write validation code, so they came up with super tight integration with Pydantic library, and with Pydantic library you can write your own Python classes, like you can see here on the top. Those are strongly typed as far as Python goes, and what it means is that when you use annotations here, you can just say that your endpoint takes as an input some class and outputs some other class. And thanks to that, you get two things. The first thing is that you get automatic validation. So if you send a simple request, as you can see right now, to this endpoint, if it's okay, then it's okay. But if it's not, then you already have built-in validation with super insightful error messages. For example, if you send invalid requests, such as this one, that is not compliant to our input data, FastAPI will automatically generate the response code for you, and it will say, okay, those fields are missing in the body of the request. Please do something with that. So that is one thing. And the second thing that you get from this strongly typed kind of a thing is you get automatic documentation. So you can just open your server, go to /docs, and it will open this automatically generated UI for you that you can, for example, use to show to other teams that, hey, we serve this machine learning model here in this endpoint. Here, just go to /docs and you will see how to use it. Super nice thing to make cooperation easier. And one additional thing that there is like a consequence of the fact that we are using those strongly typed classes is that FastAPI is able to automatically generate OpenAPI spec, not to confuse with OpenAI. It's OpenAPI. And OpenAPI spec is a standard of defining how services are exposing their endpoints. And basically, it contains all the information about what endpoints are in the server, what are the output and input schemas for your requests, what is the body structure, and so on and so on. And you can actually take this whole giant JSON and give it to someone else, and they can, for example, generate clients for your APIs in Java or C# or any other languages without any additional things, because that's a pretty well-known standard and is applicable and it's used everywhere. So great, we already have at least some things to put on our Christmas tree. So we got validation and autodocs. So now let's plug in the model. So I've decided to refactor my model a bit and put it in a separate class. Although it's simple, it kind of resembles all of the usual models, because usually you will have some class that has predict method, and then in this class usually you need to load the model in some way from some file on the disk. And this is basically what you can do here. But if you do this like it's shown on the slides, you will encounter the following problem. So every time you send a request to the predict endpoint, the model will be loaded again and again and again. And that's bad, because maybe if the model is small, then it will not take so super much time. But if the model will be larger, then you will be wasting a lot of CPU time and a lot of resources just to load the model without even predicting on it. So how to handle that? So in FastAPI, you have this concept of lifespan. And lifespan is basically a function that you define as a context manager in Python that you can see on the screen right now. And this approach allows you to plug in some functionality as soon as the server starts. Then you have a yield keyword, and then you can plug in another piece of functionality when the server stops. And what does it mean? It means you can actually put all of the heavy lifting of, for example, loading the model into memory into this lifespan. So as soon as the FastAPI server starts, as you can see in here, it will say, okay, loading the model. And now every time you make a prediction, you just take the model from the loaded ones and then just make predictions. Okay, so what if our model grows, and what if our model is larger? For example, let's say we want to serve some neural network that has a few hundred megabytes in size, which is still not super huge, but let's say it takes 1 second to execute, or 2 or even 5 seconds to execute, as in the example that you can see on a slide. So now there will be a quiz for you. So here is a code. Although it's long, let me explain what it does. So let's start with the main. I'm creating a process pool in Python. So I'm spawning multiple processes. In this case, and there will be 2 processes needed because there are only 2 tasks. And here is basically a simple request to this endpoint, to this predict endpoint that measures the time, how long it will take to for this code to send a request to my model and then gather the response and show the timing on the console. So basically a poor man's performance test. So the question for you, what do you think would be those response times? We are sending 2 requests at exactly the same second. And what do you think? FYI, the model that I'm plugging in here, if you didn't catch that, was 5 seconds. It takes 5 seconds to execute this model. So what do you think? No. So although those 2 requests were made in parallel, the first request took a little more than 5 seconds because 5 seconds was only pure execution of the model and there is some overhead on top of that. But the second request sent at the same time took 10 seconds. Do you know why? So basically by doing these predictions like this, we start async IO loop. What does it mean? So as I mentioned, the most important thing when it comes to FastAPI performance is this async IO operation. So all of the operations can be asynchronous. So if there is some IO, those can be offloaded. But our model is CPU bound. So that means whenever we are executing this piece of code in our async IO loop, it will basically starve the FastAPI server. And what's even worse is that it's not about this endpoint itself, because if you add another endpoints like the health check that I showed you in the beginning, until this model predict is finished, all of the other requests will be also postponed and the clients will not be able to connect to your model, which is super, super bad. And fortunately, there is an easy way around that. So what you can do is basically just call async IO to thread, and that will yield the execution from the main async IO loop and the model predict, which is the function that I'm passing here, and the input to it here. This will be offloaded to separate thread, and our FastAPI server will be able to serve next request easily. So in here, you can see that actually I was able to send the same requests again and get a response almost in 5 seconds. And it's not exactly 5 seconds because Python is by design single threaded. It's at least still in 3.12. They're changing that. And the overhead you can see above 5 seconds is due to the context switching, basically. So the more you request will spam to the server, the responses will be further and further from the original 5 seconds, but still it's a good way to remember about not starving the IO loop. So we got to know next few things. We got lifespan events for loading the model and event loop for our tree. And we actually right now, if you catch that, we put the model there, so there's a star on top, but the tree is far from complete, as you can see. So let's go further. So how to launch it and how to deploy it. So in the recent version of FastAPI, they've introduced a CLI that is super easy to do, and finally you can get rid of all of the difficult stuff related to deployment. You just call FastAPI dev on your local account, on your local laptop, that will basically monitor your files, and whenever you make a change to your code, it will automatically reload the whole application, which is super nice. And for serving this in prod, you have FastAPI run instead of dev, and then you can serve your model easily. So let's deploy. And what is the best way to deploy software in 2024? it's not when, it's what is. So the best way to deploy software in 24 is basically Docker. So just a matter of composing a simple Docker file with Python, and then thanks to the CLI, you can just set the command to your Docker file to run this FastAPI CLI. And having the Docker, we are now ready to deploy it and to scale the server. And there are two different ways you can scale the model serving with FastAPI. So the first one is on Kubernetes, which is super common. Most of the companies use Kubernetes nowadays. So you can deploy a FastAPI application as a simple deployment, and you can put a service in front of that. Optionally, you can add ingress to control the traffic. And on the other hand, when you want to scale it up, you can just plug in HPA, horizontal pod autoscaler, on some metric. And usually in native Kubernetes, you can only scale on CPU, which, to be honest, it's not the best way to scale your model serving applications. It's far much better to actually use something different. And that's why I've put KEDA here, which is Kubernetes event-driven autoscaler. It is like a next iteration or improved version of the native Kubernetes scaler that allows you to, for example, use Prometheus metrics to capture latency of your service and scale up your instances based on the actual application level metrics, not just CPU usage, because CPU usage itself is usually super laggy, and the autoscaler is really slow to respond to the CPU usage, while here you can actually measure in your application, your FastAPI serving code, how long does it take for a model to respond. And if that value increases, that means you are ingesting more and more requests into the same instance. That will be an event for the autoscaler to bump up number of your instances. That is super convenient. And one important thing to remember here, FastAPI command has this workers thing, and for Kubernetes just set it to 1 because it duplicates number of processes running the server. And what does it mean? In Kubernetes, you usually want to have one process with server running in one pod, so just keep in mind to set it to 1. But you can set it to something more if you're not running in Kubernetes. So basically, by using this workers command, you will be able to scale up this server. And keep in mind that by using these workers, you're duplicating the memory. So if your model takes 1 gigabyte of memory and you set workers to 4, that means at least 4 gigs of memory are needed to run your server now. Okay, so far this tree hasn't changed, but we need to have a way to look at our server and monitor it somehow. So that's where the tracing and observability comes into place. So by tracing and observability, I mean two main things. The first one is being able to do first and foremost logging and being able to see in your logs which logs were relevant for this particular request. So that's how you usually obtain it by basically attaching a unique request ID to all of your requests. And then when you log something in the debug mode or even in the info mode, you attach this unique identifier of your specific request to be able to then capture those logs and understand what was happening. Because once you, for example, if you are using Kubernetes and if you have hundreds of instances running the same thing, you will have a lot of logs that are meaningless unless you put this request ID, and you will be able to trace it down in your logs. Plus, another thing is correlation ID. This is optional, but also useful for production model serving. So correlation ID is basically usually a header that you attach to your endpoint that someone else sends to you. And you can use the same correlation ID in those logs so that you will be able to see, okay, so for example, if one client of my model server started a request and I received it, they create this correlation ID, and you use the same correlation ID in your logs. So that means when you monitor your system, you will be able to see the logs both from the client side and from your model side. And next thing that is also a good practice that we do a lot in our model deployments is saving of inputs and outputs, and also saving of the intermediate data. And what I mean by that? So saving of the inputs and outputs means basically whatever is sent to your server and whatever you respond, you save this information either fully if the scales allows you to do so, or in a sampled way. Why? That is basically for later on for you to be able to collect some data from production and be able to, for example, craft new training data sets on top of that. And intermediate data, in here, what I mean by intermediate data is that imagine I'm sending a request to a server. So there are, like, let's say it's a simple regression model that accepts some features, some numerical features. And when you send those features to your server, this is the input to the server. But input to the model can be something totally different because you can have feature engineering inside of the model serving code, which is usually the case. And those the data in the requests can be something slightly different from the data that is actually executed in the model. So the features that are sent to the model is the intermediate data that I mentioned here. So in how to actually efficiently implement that in FastAPI. So all of the things that I've said already, the request ID, correlation ID, and saving of data can be handled efficiently and really really nicely with middleware in FastAPI. So middleware is a function of FastAPI that allows you to intercept all of the requests that are sent to the server. So the idea here is basically when a request comes in, you can save the request, you can call next, which means execute the model prediction, and then save response. But don't do this like this. Because if you do this like on the previous slide, you will basically block execution. You will block execution of the model until you save the request. And that's actually bad because if you want to save this request, let's say it's a JSON to some storage like S3, until it will be saved, you will not be able to process your request and you will not be able to execute the model, which is total waste of time. So what you can do instead is you can do background tasks. So in FastAPI, there's a concept of background tasks. They allow you to schedule some functions that will be executed after the response is sent to the client. So here we are executing the model first, and we are scheduling background tasks to save request and response in the background. FastAPI handles background threads for you, so those functions will be executed at some point in time. Okay, and for monitoring, I like to keep things simple. There's a great library that we are using in prod, and it never failed. It's a thin layer of integration between FastAPI and Prometheus metrics. So once you install this Prometheus FastAPI instrumentator, you can just plug it into your app, and in the /metric endpoint, you will get all of the necessary things to monitor your model and monitor your server. So basically, you will see all of the latencies, all of the request count, how many bytes did you process, and so on and so on. Those are the metrics that are great in, for example, for the autoscaler that I've mentioned already. So yay, we are almost at the top. So we've added metrics, we've added observability and tracing by using middleware. That's awesome. But it was model serving like 101. What about doing it even better and at larger scale and handling heavier models and so on, and increasing basically our requirements list of doing serving the right way? So what topics are relevant to more complicated model serving? So first and foremost, you can plug in larger models, and larger models usually mean more problems, more memory requirements, more CPU requirements, maybe GPUs even. Batching is basically allowing you to utilize, for example, if you have model like, let's say, neural network that processes something in batches, neural network will execute as fast for one example as if it would, for example, for 10, if your GPU is large enough. So you can, for example, schedule 10 examples to be predicted at the same time with a neural network, because they are able to process in parallel. But with the approach with FastAPI, it's kind of not possible right now, because we are sending one example at a time. There's no built-in functionality to handle that for you, and you probably don't want to build this on your own. Authentication, so securing your endpoint. If you are not running internal services, then you should actually do some authentication layer, and obviously some API standards. So basically, you need to conform to some contract so that, for example, all of your services will behave in the same way. And that's where, to address all of this stuff, that's where the LitServe comes into place. So LitServe is basically a model serving library built on top of FastAPI that brings a lot of additional stuff on top of FastAPI that you probably don't want to spend time building on your own. And here's the example of LitServe API. So instead of writing the prediction endpoints directly, you can just implement a class. You can implement a setup that is a resemblance of our lifespan before. You can implement predict, and you just pass this class as a input parameter to LitServer, and you can see all of the stuff that I've mentioned. So accelerator like auto or GPU, workers per device, max batch size 10, and OpenAI spec. And how it will work, how does it work internally, why it's performant. So they've introduced the concept of workers, and the workers is basically not the workers that you saw before in the FastAPI run. Those are different workers. Those are the workers that are separate processes in the same server, but the role of those workers is only to serve your model. So they, instead of loading the model directly in the server, they're spawning a server and another processes where they load the model, and the model lives in this process. And whenever a request comes in, it goes to the request queue, that is internal request queue in the server. And from this request queue, they are able to scale up to as many workers as you want to, because they can just grab in data from the queue, process it, and put it back in the response queue and send it back to the client. And with this kind of architecture, the simple idea that they employed there, they were able to implement the batching. So again, let that sink in. So batching is where you have one model that processes multiple inputs at the same time. And it's especially useful with serving large models such as neural networks, because you can, for example, process, let's say, one image on the neural network or two images at the same time because of the GPU parallelization. So how they are able to achieve that? So this will be like a slightly interactive diagram right now. So we have two requests happening at the same time, and they are put on the queue. And once they are put on the queue, those two request handlers are awaiting for the response to appear. And from the perspective of a worker, it is able to right now dequeue more than one item at the same time. It is able to process those items in parallel, and once it completes the processing, it puts it back to the response queue, and those responses are now unlocked and they can be sent back to the clients. Okay, that's how the workers work, basically. From the authentication perspective, it's just a matter of setting right environment variable and you get authentication for free. It's simple but effective, no code changes required. And last thing is the standards. So they have built-in standard for OpenAI right now, which is conforming to the big JSON that you can see on the slide right now. This is the most common format nowadays that you usually send a request to ChatGPT or whatever. And by specifying this spec, you are automatically conforming to this API, and you can use the same abstractions that they give you to enforce some standards in your company, for example, and reuse the same standards. There are some additional things that you can check out on your own. So basically some callbacks, streaming support, and basically bring your own code because you are implementing a class there. So that means you can still have full control as you would do with FastAPI. But there are some gotchas. So LitServe is still young and not really battle-tested framework, in my opinion. It's like less than half of a year. And at the same time, it's built on the FastAPI, so you can have most of the FastAPI abstractions, but some of those abstractions are taken out from you. And one of those abstractions is, for example, the routing. So if you have, for example, /predict and /predict whatever with some changes, you cannot do this with LitServe. So bear that in mind. And with LitServe on top, our journey is complete and everything is awesome. And now you can take a deep breath, relax, take out your phone because there will be some QR codes for you at the end. And before I finish, I would like give you 3 takeaways from this presentation. So FastAPI is great for model serving if you use it wisely. And on one hand, it gives you super and great amount of flexibility. You can do many things and you can do them as you like them to do, but at the same time you are keeping the full responsibility of what you are doing, and with simple mistakes such as the one with a async loop, you can kill your server really easily. Remember to always trace and monitor your stuff. So with one server, it's usually easy to debug, but once you start scaling things, it starts to get really, really difficult. So remember about monitoring and saving responses and having at least this request ID. And pick the solution based on the model characteristics, because for simple models, you can go with FastAPI directly, but for the larger models, you might refer and go to the more sophisticated solutions like the one with workers and LitServe. And that's basically it. Those are some extra materials. Totally by coincidence, on our YouTube channel, there are 2 tutorials related to both FastAPI and LitServe. Yeah, you can also subscribe to our mailing list. All of the slides and all of the code that I've used today and in all of the previous tutorials is also available there in a shared Google Drive. And with that in mind, thank you very much for having me. That was Model Serving 101.
Thank you, Marcin, for this presentation. So now there is question time. So if you have any question, please raise your hand and I will come with microphone.
Thanks for the presentation. What is the benefit of using async endpoint and to thread instead of just using synchronous endpoint, like without specifying it as async if this is predict method?
Yeah, so with a synchronous endpoint, you would have to do some to-thread anyway in order not to block the server. Because with not async endpoints, you immediately block the async IO loop because those not async requests are still running in the async loop.
Thanks for the presentation. I have the question about the batching. So from your experience, what's the good approach for processing many requests? Like, for example, we have 2 users, they send some requests in the same time, but we have max number of requests that we can get into the queue set to 10. So should we wait for some time for another request, or or should we just process it after some time? And yeah, so how do you think how it should be done?
Yeah, great question. So in this batching approach, so you have this this timeout here. Actually, sorry, not timeout. Those are the awaits that are waiting for the request to happen, and the worker queue here, worker process here, actually has two parameters. The first one is how many batches, how many items to accumulate in a batch. And the second parameter is how much time to wait before doing any processing. So that's the parameter you probably want to set. So for example, you can have at least 10 items, or if it's not 10 items, then max wait time 5 seconds, because otherwise your clients will get angry. So even if there will be not enough requests to process, this timeout will be exceeded and you will process those requests anyway.
Yeah, I think that's it. Thanks for the explanation.
Hey, have you ever used LitServe in production?
No.
Okay.
And what you see in here is because I wanted to know how they actually approach this stuff. Because I didn't want to use LitServe right away because it's not production ready. In my opinion, it's too early for us to use it. FastAPI is much more mature. And this implementation is super nice and I'm going to steal it.
Okay, so and you're gonna implement that in FastAPI, or for example, because there's, I think going even further, you can even have like an inference server, for example, Triton, or something like that, and it also has like request batching and everything, and it's completely separated.
Yeah, personally, I don't have experience with Triton, and we are not serving super huge models to use Triton. So maybe next year.